And the Carnot cycle, or the Carnot engine, goes through 4 cycles. And the first cycle, wherever my gas happens to be. Now, when we're thinking about an engine, the simplest engine is a canister of gas with a piston. And then if I put that gas in contact with a hot reservoir, that gas will expand and do work on the piston. And then if I remove that and put the engine in contact with a cold reservoir, the gas will shrink and the inertia of the piston will continue and push the piston down. So I'm going to get the piston to just continually move up and down. If I put it in the hot reservoir, the piston's going to move up. And then when I put it in contact with the cold reservoir, the piston is, its own inertia is going to cause it to then move back down and do work on the gas. All right. So there are 4 cycles here in the Carnot cycle. And the first cycle is that I put my engine in contact with the hot reservoir and I let the system move in thermal equilibrium. So that means that the temperature stays the same throughout this entire cycle. So this is an isothermal expansion. I put my engine with my heat reservoir, my hot reservoir, and the heat moves through the gas, but it does so isothermally, and so the gas expands isothermally. So the first part of the engine is isothermal expansion. Then we remove the hot reservoir, and again, the inertia of the piston is going to move if the piston, imagine the piston is connected to a crankshaft. And so as the crankshaft is moving around, it's going to just keep moving the piston with it. And because we have removed the hot reservoirs, there's nowhere for the energy to go, so the energy does not leave or enter the system, so this is now adiabatic expansion. Then we have isothermal compression, because at this stage we move the engine to be in contact with the cold reservoir, and it will reject some heat to the cold reservoir. And so again, we're going to do this so that the system remains in thermodynamic equilibrium. So this is isothermal compression. And then finally, we're going to have adiabatic compression. As we remove the engine from the cold reservoir, the piston is going to continue moving with its own inertia and continue to compress the gas. But again, energy is not entering or leaving, so we're going to have adiabatic compression. Okay, so these are the 4 steps of the Carnot cycle. And again, these 4 steps define the maximum efficiency that a true engine can have. It cannot have a greater efficiency than the efficiency of this cycle between 2 hot and cold heat reservoirs. All right. Okay, so this Carnot cycle might look something like this. The gas starts at point A and it goes through isothermal expansion to point B, where we remove the heat reservoir. So here it's in contact with the heat reservoir and it draws in heat QH. And then we remove the heat reservoir and it continues to expand adiabatically and out to point C. And then it will compress isothermally from C to D, and that's when it's in contact with the cold reservoir QC. And then it will compress adiabatically from D back to A. All right, so this is the typical Carnot cycle. Now, how can I find the efficiency of this particular engine? Well, remember that the efficiency, we can write it like this. So if I can find the amount of heat pulled in, I can find or the amount of heat pulled in and the amount of heat rejected, then I can use that in this manner. How do I do that, right? Well, remember that the amount of heat is equal to the specific heat of the gas times the amount of gas that I have times the temperature difference, okay? But also remember that that's the basic definition of heat and heat capacity, but for an isothermal expansion, it stays at the same temperature, right? It stays at the same temperature. But remember that we did have an expression for the amount of heat to expand or compress something isothermally, and that expression was this. Right? If I'm doing work on a gas, remember that work is equal to P dV, and if I use the ideal gas law and insert nRT over V in for P, and I integrate, then I get this. So this allows me to calculate the amount of heat that has been transferred to the system from the hot reservoir between points B and A. So we can say Q hot is equal to nRT ln. Let me put it over here. Okay, so the amount of heat that I'm going to draw in is going to be nRT ln VB over VA, and the amount of heat that gets rejected is going to be nRT ln of VD VC. Now, the T here is also the temperature of the hot reservoir, and the temperature here is also the temperature of the cold reservoir, okay? So we need to make sure that we have that written down as well. We don't want to use the same temperature for both calculations. That would be nonsense, because the temperature here is obviously, well, the temperature as we're gaining from the hot reservoir is going to be much hotter typically than the temperature at the cold reservoir, okay? So the TH and the TC are imperative. And we insert the negative sign here because we know this is heat being rejected from the system back to the environment, okay? Now, you can actually play a bit of a funny game, and your textbook goes through it. So I'm not going to do the derivation, but if I were to take C over QH and manipulate my variables, NR and NR are obviously going to cancel out. You can flip this ratio to get VC over VD, and that gets rid of the negative sign. And then you can play a game with the volumes that causes them to essentially disappear, and the end result is that if you just use the temperatures, you get a very similar expression to the heats, okay? So again, I'm not going to go through the derivation, but there you have it. So you can define the efficiency by either the amount of heat that you actually pull in units of energy, and the amount of heat expelled in units of energy, or you can just use the ratio of the temperatures. What's the temperature of your hot reservoir and the temperature of your cold reservoir? In the next video, we'll actually do a specific example with the Carnot cycle and see how to actually do some of these calculations. We'll see you next time.